So we want to make a projectile calculator, and in order to do that, we have to use our projectiles to put in a spreadsheet to do the calculations for us. So these values here that are in blue, they are things the user will enter. So the user is somebody who needs to calculate how far a projectile goes, but they don't know any physics. So all they're going to do is punch in these numbers here and possibly an acceleration in the x direction. And we're going to write formulas to figure out all these other things. So the first one is the easy one. To find out delta y, we just need to take the final height where it lands minus the launch height. So we're going to write a formula right here. We're going to click in this cell and type equals. And then we're going to click on this cell right here, so it'll put in B5 minus this cell right here, B4. So if you take B5 minus B4, you will get delta y. So if it starts at 30 and it lands at 0, you get negative 30. That's what you would expect. If it starts at 30 and it lands at 5, then you would expect delta y to be negative 25. So no matter what numbers you put in here, delta y will always be calculated. Now the next thing we need to do is find the velocity in the y direction initial. So our equations told us that to find the velocity initial in the y direction, we had to take the initial velocity, which is right here, right there, and multiply it by the sine of this angle. So we're going to write a formula right here, okay? And right up here, you can see the formula that I'm typing if you can't see it in the cell. So this cell is going to equal the initial velocity that the object is launched at, so that's B2, times the sine of the angle. The only problem is the angle here is in degrees, and the spreadsheet has to use radians. So inside the parentheses, I'm going to type radians, and then I'm going to click on this cell. So radians of B3 converts B3 to radians, and then I'll take the sine of it, and then I'll multiply it by B2. Okay, so this is how we find B2 is the initial velocity times the sine of the launch angle, and that converts it to radians. So there's the equation right there you need. And when you do it correctly with these numbers, you should get 33.46. We are also going to do that in the x direction. So in the x direction, it equals the initial velocity, which is B2, times the cosine of the angle that it's launched at. But again, we have to convert that to radians. So we type radians, and then we click on B3. And so there's our formula for that cell right there. Okay, we're going to take B2 times the cosine of the radians of B3. And that gives us 37.16. And then you'll notice if we change these things, like I launch it at 20 degrees, you'll see these numbers actually change. It's automatically doing our calculation for us, okay? All right, the next thing we're going to do is figure out the acceleration in the y direction, and that's easy. It always equals -1 times the gravity constant. Okay, so this cell right here equals -1 times B6, and that tells us the acceleration is -9.81. All right, we're now ready to solve the quadratic equation to find the time. So remember the quadratic equation, we did this in class a lot, but A was always 1/2 of the acceleration in the y direction. So this is going to equal 1/2, so 1 divided by 2, times the acceleration in the y direction. That's always A. B was always equal to the initial velocity in the y direction, so B just equals h3. We'll ignore that autofill. And C was always negative whatever delta y was, because remember we had to bring delta y to the other side. So C will equal -1 times delta y, which is right here, h2. So there we have the coefficients of the quadratic equation that we're going to solve. And now we need to write the equation for the quadratic equation. Okay, so this is going to get kind of big. So you may have to pause the video to get it all, but here we go. It's going to equal, and we're going to open parentheses to start the numerator, and it's going to be minus b, so minus this cell, that's b, and that's plus or minus, so we're going to use minus the square root, so I type sqrt, open parentheses, of b squared, so that's this to the power of 2, minus, and you can't see it anymore, it's running off the video over here, but you can see it up here, okay? So it's minus b minus the square root of b squared minus 4 times a, which is k2, times c, which is k4, end the parenthesis, that ends the square root, end the parenthesis on the numerator, divided by, open parenthesis, 2 times a. So the formula you're looking for is this big beast right here, okay? And that is the quadratic equation using a, b, and c coefficients. And when you do all that, you should get 7.38 for this problem. And of course, if you change anything here, that should automatically update. So if we put in a launch velocity of 20 instead of 50, you'll see the velocities in the y and the x direction changed. These all changed, and now it's 4.11 seconds, okay? So we'll go back to 50 here. All right, once we know the time, we can say that this time here simply equals that cell. And the same thing is true here. This simply equals that cell. So whenever this cell gets changed, those do also. All right, we're almost finished. To find the range of the projectile, we have to, first of all, find the, we know the acceleration in the x direction. So to find the range of the projectile, we say equals, and let's just, there we go. So it equals the initial velocity in the x direction, which is e3, times the time, and then plus 1/2 times the acceleration in the x direction, which was usually 0, because you could ignore it usually, but if it wasn't 0, you'd have to do this. So it's 1/2 the acceleration in the x times the time squared. So there again is the equation we're typing in there. And that calculates the range. And you can put in any problem we've solved, and it should give you the answer. So our introductory problem was a launch velocity of 50 meters per second at 36.8 degrees from 0, and it went about 245 meters. So there we go. And it was in the air about 6 seconds. So there we go. That's the one we did on paper where we plotted the path of the ball. All right, we are almost done. To find the final velocity in the y direction, we take the initial velocity in the y direction, which is h3, plus the acceleration times the time. Okay? So that's one of our equations from Unit 1. The final velocity is the initial velocity plus the acceleration times the time. We do the same thing in the x direction. The final velocity in the x direction equals the initial velocity in the x direction plus the acceleration in the x direction times the time. And of course, if there's no acceleration in the x direction, the final and initial should be the same. The max height was a problem we solved in a couple of assignments. So to find the max height, we have to stop the problem when it's at its maximum height, where the final velocity in the y direction is 0. So it turns out that to find the maximum height, we have to do this. We have to take, in our numerator, the final velocity squared. So at the maximum height, the final velocity is 0, minus the initial velocity squared. All of that is divided by 2 times the acceleration in the y direction. And that will tell us how much the ball goes up. To that, we have to add the height at which it was launched. And that will give us the maximum height. So if I go back to 30, 42, and 50, if I launch it from a cliff that is 30 meters high at 42 degrees, the maximum height is 87.5. Okay? So doing all of that and getting it working will get you 18 points. Please do not type these numbers in the cells, because when I grade it, I will put in something different here, like a launch angle of 15 degrees, and these will all have to change because you've written formulas. If they don't change, then I know you just typed in numbers, and that's not going to work. Okay? All of that will get you 18 out of 20 points. To get the last 2 points, you have to make a graph. There's a hint on the Canvas page there, but it's up to you to figure out. Okay, so to get the last 2 points to get a perfect score, you're going to have to really work a little harder on your own. All right, good luck.